Well, a basic statistical model has a target variable y and there are set of predictors of features, right? So there are different names. Some call it independent variables, some call it features, predictors. So you can name any one of these names. So how many features you should have in the model? Often an important questions in any statistical model. Okay, so the one important thing to consider is uh, you have to consider the prediction accuracy, or the trade-off is between prediction accuracy versus model interpretability. Why is so? Because when you use a large number of variables, the prediction accuracy is likely to go up. Okay, but the interpretability of the model will go down. Okay, so that's the main issue or the main trade-off that lies selecting the best number of predictors in a model. Okay, so the idea is how many features or how many number of independent variables or predictors are to be there in the model. Okay, so the trade-off is whether to have less number of features or more number of features. If you have less number of features, it's easy to interpret, less likely to overfit, low prediction accuracy. So these are two good points, but the third one is the bad point or the cons, right? The first two are the pros. If you have more number of features, you should will have difficulty in interpreting. So that's a con, that's a demerit. Then it's more likely to overfit. That's again a bad thing. But we are likely to have high prediction accuracy. Okay, so that's a good thing. So how do you know that what is the best set of variables or best set of features which does justice to both prediction accuracy as well as model interpretability? And that's the idea behind this session. So what are the ways to do or select the best number of features, and how to select the best model out of this given set of features, given set of models. Okay, so feature selection can be very important in model building. So if you look at the way we measure the performance of machine learning or statistical model, it actually depends on following points. Okay, it depends on the choice of algorithm, the algorithm that we are choosing for to build a particular model or to solve a particular problem, the feature selection uh, or the method feature selection method that we are using, and we'll see in the next slide what are the feature selection method available to us. Feature creation, important thing. So how many new features or new predictors that you're creating from the given set of predictors, right? So that could be many, right? For instance, if you have x is one of the predictor, you just created by squaring it, that's a new creation. You can take the log of it, so that's again a new feature. So that's nothing but feature creation. And then the finally it's model selection. So your prediction accuracy or the performance of your model, both in terms of interpretation, prediction, more from a prediction point of view, it depends on the choice of algorithm, feature selection, feature creation, and model selection, right? And one of the most important thing is feature selection, and that's what is the topic for this session. Feature selection is also known as variable selection. Okay, in ML we call it feature selection, but it's more or less the same. Okay, so what are the feature selection methodology available to us? This basically can be categorized into three types. The first one is filter methods. The second one is wrapper method. The third one is embedded methods. Okay, and these are groups of methods. There are several techniques within each one of these groups. Okay, so what is filter method? Okay, so filter methods have several types of selection methods, and it's also known as single factor analysis. So in econometric modeling or pure statistical modeling, people call this as single factor analysis. Well, so what we do in this method or in such methods rather, because there are several methods out there, it's not just one method, and this, remember, this is just a group of methods. We calculate or we compute the predictive power of each individual variable. So instead of combining, we just calculate, or we just measure the predictive power of each individual variable. So we evaluate that. Okay, so how do you do that? Well, several ways to do it. Correlation, we find out the correlation. So we find out the correlation between target variable with respect to the predictors or the features, the x variables, right? Whether it's x1, x2, or so on, right? And we have y as target variable. So we find correlation of x1 with y, x2 with y, x3 with y, and so on. Now, intuitively, the independent variable or the feature or the predictor, okay, I'm going to use just one of these name. So the feature that will have the highest correlation with y is the best feature, okay, because we want the target variable to be highly correlated with the features, right, or the predictors, right? So that's one way of finding it out. So you just find a correlation matrix where you will have y, and then you will have x1, x2, x3, and so on, and see which one of them is having highest correlation. Correlation, by the way, lies between 0, 1, 1. So the one that has the maximum, whether it's negative correlation or positive, or the modulus of correlation, whether it's positive or negative, doesn't matter. The one that has highest modulus of correlation is the one to be having the highest predictive power. Okay, so here x1 has highest, x2 followed by x2, and then x3, right? So that's one way of selecting the best variable. So you can take the top two variables to be having good correlation and go ahead with doing your modeling. So drop x3. There's no reason to do that, but you might consider that. So that's one of the many ways of selecting variables. Information value. So this is this comes from the more from industry point of view, not from academics point of view. So in industry, people use information value, which is some sort of a transformation of your independent variables, and which finds out the ability of the independent variables or the features to discriminate your y variable, or ability to predict y variable. Okay, so the one that has high information value is to be selected. Similarly, chi-square statistics is also used for categorical variable, or more suited for classification problem. Oh, sorry, categorical independent variable, or categorical features. Okay, not target variable. All right. So the conclusion that we have drawn from the the filter methods is that the one which has high correlation with the target variable is going to have the highest preference in the model, with low correlation between predictors. So ensure that not just high correlation with the target variable, also have low correlation with independent variables. So x1 and x2 should not have high correlation. So that's another point to be considered. But then here, in filter method, you don't actually look at two variable at once. You just look at just one of them and compare that with your y. So it's more of an univariate analysis. Higher the IVs, better is the variable. Okay. Okay. Wrapper methods uses combination of combination of x variables or features and find out which one is the best combination. So instead of finding out the best variable, it find out the best combination of variables. Okay. So predictive power of variables is evaluated jointly. Okay. So we can say that, okay, jointly x1, x2, and x5 are the best features among the set of 10 features. Okay. So that's the way we analyze this. Okay. So it's a joint evaluation of variables. And there are several methods available to us. One is subset selection, second one is forward selection, third one is backward selection, and we'll see each one of them, and we'll also take an example and do it in R just to give a demo of how this method works. And in embedded method, which is the third one, we'll also talk about it in brief. We'll go to the details of it, but we'll talk about it in brief. So this is an inbuilt variable selection method, so we don't have to take any decision. So in wrapper methods, we have to take a number of decisions, and I'm going to talk about all these three methods. So we'll see that several decisions have to be made um, while doing this analysis. Whereas in embedded method, the decisions are taken by the regression algorithm or the estimation algorithm. So it's very much inbuilt or automated type. Okay, so it's easier to use. So without one having to select or reject. So one may not have to select or reject a variable, right? So algorithm does that for you, and that's one of the technique of selecting the best features. It's also known as regularizations, and what I've heard about regularizations. So it controls the value of parameters. So the not so important variables are given very low weight or sometimes zero weight, and that's why they get eliminated from the model. So the elimination process is very much inbuilt or very much automated. So you are, as a modeler, need not have to take a lot of decisions. So it's also known as shrinkage method. We'll talk about it. The famous ones are lasso and ridge regressions. We'll talk about it in brief at the end of this, at the last part of the session. So the idea is to have optimal number of features. Okay, so that's the point. So an ideal model should have good prediction and yet not very complex to interpret and use or to implement. Oftentimes in industry, you have problem of implementation or interpretation, right? So if you're building a model which, let's say, it's an image recognition model, right? It's more, used in tech companies, image recognition. Their implementation may not be a challenge. Okay. Because you have good infrastructure, you have a very high infrastructure to cater to high dimensional space, that's okay. But if you are building a model in banking, rather evaluating or quantifying risk in banking or financial or insurance organizations, it's very difficult to implement overly complex models. Regulators are going to have questions. Even your business people in business who are going to use your model are going to find it very difficult to use your model, given that you have made it very complex. You have so many predictor variables, you have so many variables artificially created, so that's going to be difficult. So the idea is to have a good prediction and simple model, right? So we'll use subset selection, shrinkage, and dimension reduction, and we'll talk about